Good morning, boys. I'm really sorry I can't be there today. I'm not feeling the best. Hope I'll be back in tomorrow or the next. Today, we're just looking a little bit at the zero index with a bit of review of some of our other laws. On the screen here is out of our textbook. It will be a good idea to copy this down, and you can have some opportunity to pause this video, of course, at any point in time to do that, or it's simply from your textbook. I'm going to talk about each of these laws very briefly. The second and third law you should be very familiar with now, okay, because we've done a lot of work with not just numerical bases, but with algebraic bases when we are multiplying or dividing those base numbers. We're going to be working a bit more on the index law for power of power and also the zero index, which we have spoken about. Now, I'm just going to do a couple of examples, okay, which is going to say something like simplify, something like 5 to the power of 4 times 5 to the power of 3. And then I'm going to do 8 to the power of 10 divided by 8 to the power of 2. Now, I think we've done these questions with algebraic bases, okay? When we threw the numerical values in, we kind of made some errors, and that's quite common. Now, thinking on this very first question, the 5s are the actual bases. Now, think about back to our algebraic laws. I'm going to write them up on the right-hand side. We said a to the power of m times a to the power of n equals a to the power of m plus n. And so what that law said was that when we are multiplying a common base, whatever that might be, numerical or algebraic, then we simply add the powers. Now, in this instance, if we do that, we would get 5 to the power of 7, which would be the correct answer. Now, again, we are simply simplifying. We're not evaluating. We're not getting the basic number for that. We're just writing it with an indice or an index. Now, just as a reminder why this is the case, well, 5 to the power of 4 means that we are multiplying 5 by itself 4 times. There's a multiplication symbol. And 5 to the power of 3 means we're multiplying it by itself 3 times. And there you can see pretty clearly we are multiplying 5 in total by itself 7 times. And that's why our final answer would be that 5 to the power of 7. Okay, but you can see how when we expand it, that kind of works. Now, likewise, when we look at the division, we know the opposite of times is divide. Okay, so if we apply that to our law, a to the m divided by a to the n, well, the opposite of add is subtract. And so that's where we looked at that law that when you are dividing a common base, we subtract the powers. Now, if we looked at this example, 8 to the power of 10 divided by 8 to the power of 2, we would subtract the power. 10 minus 2 makes 8. And that would be our final answer. Again, we're simplifying it. We're leaving it with a power. Now, if we kind of drew this one out in a little bit longer term, although I've used some big numbers here, in terms of we've got 8 multiplying by itself 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we're dividing it by 8 times 8, which means 8 to the power of 2. Now, remember when we looked at this, we said that 8 divided by 8 was 1. So it simplifies. 8 divided by 8 is 1. So it simplifies. And there pretty clearly you can see we have 1, 2, 3, 4, 5, 6, 7, 8 of them being multiplied 8 times. 8 to the power of 8. So they're the two laws that we've currently looked at. Now, of course, as I said, we've done this with algebra. And a lot of time when we look at numerical bases, we tend to make errors because we try and multiply the 5 and the 5 to make 25, for example, to the power of 7. Or we do 8 divided by 8 is 1, and do 1 to the power of 8. Okay? We've got to be really careful with when we have only numerical bases that we don't do that. Okay? Worst case scenario, expand the numbers out like I've done here. Okay, but ultimately, we want to kind of look at these rules or these what we call indice laws. We want to use these things here to help us. So these are the two laws we've looked at. So example 2, we're now going to look at some new laws. Okay, the first one is going to say to simplify. I'm going to say 3 to the power of 2 to the power of 3. Okay. Now, what does that actually mean? Well, we know that 3 to the power of 2 means 3 times 3, right? 3 times 3. And yes, I know that makes 9, but we're going to leave it in that form. That's what, and I'm going to do it in yellow, that's what 3 to the power of 2 means. Now, what does to the power of 3 mean? Well, that means whatever's inside those brackets, we are multiplying it by itself 3 times, which means I'm going to have this in total 3 times. 3 times 3, then 3 times 3, and then 3 times 3. Now, if I wanted to write this in a shorter way, like we did in example 1, how many 3's are we multiplying by itself? Well, we have 1, 2, 3, 4, 5, and 6. So we actually have 3 to the power of 6. Now, similar to the first two rules, can you look at the question and then go to look at the answer and see if there is a quicker way that potentially you could have got 3 to the power of 6? Well, what I'm hoping you are looking at, gents, is saying, well, hold on. Could we multiply the 2 and the 3 together? And the answer to that is absolutely. And we call this power of a power law. And what this power of a power law says, I'm going to do this on the right-hand side, that when you have a common base and you are multiplying them together, oops, not like that, so when you have a common base and you are raising it to a power, so we've got a to the m, all to the power of n, well, we can actually multiply those indices together. And we call that the power of a power law. So it's a little bit quicker to do it like that. So you can see so far we've got these 3 nice laws. Okay. Now, if I do a part B, let's say we have 4 to the power of 3 all to the power of 2. What do you think this answer might be? Well, I'm hoping you said, hey, we've got 1 power inside the bracket, 1's outside the bracket. So that's the power of a power law, which means that we can multiply those indices together, and that would just give us 4 to the power of 6. Now, that would be absolutely spot on if you said that. Now, again, if we expanded it, 4 cubed means 4 times 4 times 4. And if I square something, that means that we are multiplying it by itself. And now you can see, with me having written that out, you can see very clearly that we actually have 4 to the power of 6. So we've used that power of a power law by multiplying those two numbers together to get the 6. Now, if I said C and I brought a bit of algebra into it, nothing else would matter or change. For example, if I did a to the power of 4 and I raised the whole thing to the power of 3, that would just be a to the power of 12. Beautiful. And again, that means we've got a times a times a times a, and that's happening 3 times. So you've got 12 of them going on there. Now, of course, they get a bit more challenging down the track, certainly do. But at the moment, we're just looking at those numerical bases for today. Okay, when I'm back in class, I'll take you through a few harder questions. That's example 2. And then example 3, okay, simplify. And then I'm going to look at A 5 to the power of 4 divided by 5 to the power of 4. Now, we've actually done one like this in class. We've actually spoken about this question. Now, I'm hoping when I say to you 5 to the power of 4 divided by 5 to the power of 4, you're yelling at me saying, sir, I know that's equaling to 1. Because whenever you divide something by itself, like 10 divided by 10, 2 divided by 2, 100 divided by 100, A divided by A, 5 to the 4 divided by 5 to the 4, we always come out with 1. Now, we could demonstrate that, of course, by saying 5 times 5 times 5 times 5 all over 5 times 5 times 5 times 5, and they all simplify. Okay, 5 divided by 5 is 1, 5 divided by 5 is 1, 5 divided by 5 is 1, and 5 divided by 5 is 1. Remembering, though, what we're actually left with is this. That's why I like to say that word simplify, not cancel. Because some people will say, there's none left, so it's 0. And that will be incorrect. Okay, we've just got 1 left. Okay. Now, the reason I show you that question, I know we've done it before, is that what if we used that division law from the very top of the screen? Zoom right in. What does the division say when the bases are the same? Well, it says that we subtract the power. Well, if I come back to that question and I do it a different way, and I said, well, hold on, we've got the same base and we are dividing, could that not also be 5 to 4 to 5 to 4? 4 minus 4 is 0. And that's where we get this new little concept that any base to the power of 0 is always the same as 1. And that's why it happens. Because you're dividing it by itself, the answer is 1, which means you subtract the powers, we get 0. So this is the 4th law, and this is the one of the pretty much not the last index law we have, but certainly there's not many left. Anything to the power of 0, do like this. Anything to the power of 0 simply equals 1. Okay? Anything to the power of 0 will simply equal 1. Now, with algebra, we can make that a bit more challenging, which I'll show you very shortly. But certainly, we can get questions like this. 6 to the power of 0 times 3. And it will say to simplify. Well, 6 to the power of 0, that can be replaced with a 1. And 1 times 3 equals 3. There's my answer. I could give you a slightly harder question that says 7 squared times 3 to the 4th all to the power of 0. Now, what does that power of 0 work on? Well, guess what? It works on the whole thing. So automatically, the answer is 1. Because it works on everything. Now, if we use that power to a power law, I'm just going to explain this. Power to the power law, we multiply the powers together. So 2 times 0 would be 0 times 4 times 0 is 0. And that gives you 1 times 1, which is still 1. And that kind of shows that it still holds true. So with these questions, you have to ensure you know, is just the base to the power of 0, or is the whole thing to the power of 0? And that's where some people will make those errors, because we don't realize what the power is actually working on. Okay, gents, that is the end of the lesson. Now, I'm just going to briefly remind you about our laws. Okay. 8 to the power of m times 8 to the power of n. So when we multiply a base that is the same, be it numerical or algebraic, we simply add the powers. When you are dividing a common base, we subtract the powers. If you are raising a power to a power, as such, so one power is inside the brackets, one side's out, we can multiply the powers together. And anything to the power of 0 simply equals 1. And they are all our indices laws to date. Okay, and they're very important for us to practice. Now, of course, we can do this with algebraic bases like A's, or we can simply use numerical bases like a 3. I'm going to demonstrate very quickly. 3 squared times 3 to the 5 is 3 to the 7. 3 to the 7 divided by 3 to the 4. Well, we're going to subtract those. We get 3 to the power of 3. If I have 3 to the power of 4 or to the power of 5, one inside, one outside, well, we multiply. And the very last one, if we have 3 to the power of 6 all to the power of 0, anything to the power of 0 equals 1. And so we can do it with algebraic bases. We can do it with numerical bases. You just have to identify what is the common base. And there we have our solution. Gents, I hope that made a bit of sense. Hopefully you have a bit more understanding. Again, the main thing for today are the two new ones. Power of a power, we multiply, and anything to the power of 0 simply equals 1. Now, in terms of work for today, gents, it's probably a little bit longer than I wanted that lesson to be. We've got exercise 11F. I've asked you to do questions 1, 2, 6, 7, 8, 9, 10, 12. And then for homework, to finish those off, if you haven't been able to do in class, if you have finished those off, I'd ask you to complete this indices topic test. Okay, in fact, that's the homework I want you to complete, is the indices topic test. And hopefully I'll be back tomorrow. If not tomorrow, I should certainly be back for your third lesson this week. Have a wonderful day, gents. I hope you are well, and I look forward to seeing you very shortly. Have a good day.